Okay, so we start. We talk about graphs. So just to recap, what is graph? So basically, for graph we have V and E. So V is the basically set of vertices, or it is called nodes also, and E is the set of edges. Okay, so basically there are edges is basically E is a subset of V cross V, and there are two types of graph, directed graph, undirected graph. If there is no ordering of the edge, then it is called undirected graph, and if there is a ordering in the edge, it is called directed graph. Like, so if we have vertex say V1, V2, say V3, V4, and if we have like this, so this is a directed graph. Or diagraph, because we have direction in the edges, and the vertex set is V is basically V1, V2. So basically we have V1, V2, V3, V4, or for simplicity we can just write 1, 2, 3, 4 for simplicity. Okay, and what are the edges? Edge set is basically, so we have a edge from V2 to V1. So V1 to V3. So we can say 1, 2, 3 like this. So edge is a subset of Cartesian product of V cross V. So 1 to 3. Then we have a edge from 2 to 1, and we have edge from 2 to 3, and then we have edge from 4 to 3. So this is the edge set. Okay, and this is a directed graph. Now, for an undirected graph, we are not having the direction. So like this. So suppose this is a graph. So V1, V2, V3, V4. So these are the edges. So for undirected graph, if 1, 2 is a edge, then 2, 1 is a edge like this. So this is a undirected. This is a directed graph. This is a undirected graph. Okay. So now, so in a graph, what is the cardinality of E? So E is basically order of V square, big O of V square. Okay. So because it can be at most connected, I mean complete graph. Complete graph means every vertex, any two vertex there is a edge. So any two vertex there is edge mean if there are n vertex. So if we have V say V1, V2, Vn. So if we take any two vertex I and j, if there is a edge, okay, so then there will be n C2 edge. So this is basically order of n square. So that's why order of V is upper bound by order of n square. Okay, and so this is for a complete graph. So this is the upper bound. So order of V is bounded above by order of n square. Okay, so now the question is how we can represent a graph, how we can present a graph to a computer, or how we can represent a graph. Suppose we want to give the input of this graph to a computer, we want to have a programming, we want to have an algorithm where our computer need to take a graph as a input. So for that we have to, so there are two methods basically, adjacency matrix and adjacency list. So what is the adjacency matrix representation? So let us just talk about graph representation. So this adjacency matrix, so adjacency matrix is basically, suppose we have n vertices. So this is a matrix of size n by n. So these are the vertices. So up to n, V1, V2, up to n. So, this matrix will be 0 1 matrix. So, if this is a ith vertex, this is a jth vertex. So, ijth element will be 1 if ij is an h. So, this matrix say aij is 1 if ij is an h, 0 otherwise. Okay. So, if we have a h from I to j, this is the ith vertex, this is the jth vertex. If there is a h from I to j, then that corresponding field will be 1 in the adjacency matrix, otherwise it will be 0. That means, there is no h between I to j. So, this is if a graph is undirected graph, then this matrix will be the symmetric matrix, because if undirected graph there is no direction of the h. So, that means, for undirected graph ij is also an h and ji is also an h. So, this matrix will be symmetric matrix for an undirected graph. Okay. So, for this graph, so what is the adjacency matrix corresponding to this graph? So, there are 4 vertices. So, the size of the matrix will be 4 by 4, 1 2 3 4, 1 2 3 4. So, this is the adjacency matrix. So, we have from 1, where is the h? 1, there is no h with 1. So, this is 0, there is no h with 2, 0. There is only one h from 3, 0. And from 2 we have h to 1, there is no self h. So, this is 0. So, this is 1, there is no h to 4. From 3 there is no h to any other vertices. All the edges are incoming edges for 3, vertex number 3. For 4 there is no h to 4, for 4 there is no h to 1, therefore 4 there is no h to, there is 3, sorry, there is. So, this is the adjacency matrix corresponding to this graph. Okay. And corresponding to this graph, and if the graph is undirected graph, so corresponding to this graph, what is the matrix? 3 4, 1 2 3 4. So, we have h between 1 2. So, this is 1 2 1 0, 1 2 2 we have a h. So, 1 2 3 we have a h, 1 2 4 no h. So, 2 2 2 to 1 there is a h, 2 to 3 there is a h, and 0 0, and then 3 to 1 there is a h, 3 to 2 there is a h, 3 to 3 there is no h, 3 to 4 there is a h. So, 4 to 0, 4 to 1 there is no h, 4 to 2 there is no h, 4 to 3 there is a h, 4 to 4 there is. So, this matrix is a symmetric matrix, because for undirected graph, if I j, if 1 2 is a h, then 2 1 is also an h, there is no direction of this. So, this is the adjacency matrix corresponding to this undirected graph. Okay. So, now the question is whether this is a good way of representing a graph. So, what is the drawback of this? Now, suppose our graph is sparse graph, that means suppose there is less number of edges. Suppose the graph is sparse graph. So, that means less number of edges are less number of edges. Okay. Then what will happen? Then this matrix will be a sparse matrix. That means we have our vertex is more. Suppose we have 100 vertex. So, this matrix size will be 100 by 100, and suppose we have only 10 edges. So, in this matrix 100 by 100 matrix, we have only 10 fields where we have 1 remaining as 0. So, this will be a sparse matrix. So, that means we are wasting the memory. To have represent this, we need to have a array, 2 dimensional array. If we are implementing this in C, we have to define 2 dimensional array to have this matrix. So, basically for sparse graph, this representation is not good. So, for that we just have what is called adjacency list. That is also one way of representing a graph. Adjacency list. So, adjacency list is basically, so we take a vertex and we have a linked list corresponding to each of the vertices. So, this list contain the vertices which are connected to that vertex. So, for example, if we had that graph 1, 2, 3, 4. So, we have this V1, V2, V3, V4. So, adjacency list means 1 is connected with 3. So, 2 is connected with 1 and 3. So, and 3 is, there is no, this is empty, and 4 is, from 4 we have a 3. So, this is the adjacency list. So, from each vertex we have a linked list kind of thing, where that contain the vertices which are connected with this. If it is a directed graph, otherwise if it is undirected graph, we have no direction. So, we just take the vertices we are connected to this. Okay. So, this is basically the adjacency list representation. So, this is good if our graph is sparse graph, because in that case we have only few vertices. So, that means we have the list contain few number of edges, a few number of nodes. So, that way it is good, but if the graph is dense graph, if there are more edges, then this will be a huge list. Then it is good to go for a adjacency matrix, because that is a 0 1 representation, just the bit vector 0 or 1. Okay. So, that is very nice data structure, just a 0 1 representation. So, if it is dense graph, that means if the number of edges are more, then we will go for the adjacency matrix representation. Otherwise, if it is a sparse graph, if the number of edges are less, one can go for the adjacency list, because in adjacency list we have to go for the linked list ring list implementation, but matrix is very easy to handle. Okay. So, this is basically two way we can represent a graph, either by the adjacency matrix or by the adjacency list. Okay. Now, we will talk about some graph problems. So, first graph problem we talk about minimum spanning tree problem. So, let us talk about minimum spanning tree problem. Minimum spanning tree problem. So, for this, what are the input? Input is a basically we have a undirected graph. We have a graph G, which is basically a undirected graph, and we have a edge weight on the edge. So, we have a weight function W, which is coming E to R. Okay. So, W is a weight function. So, we have a edge weight. Okay. So, now for example, suppose you have a graph like this and this. Suppose you have a graph like this, and we have some weight over here -3, 4, -5, 6, -2 say. Okay. And these are the vertices V1, V2, V3, V4. So, this is the weight function. So, W of I j is basically, if I j is an, so weight, so if I and j is a vertex, 2 vertex, and if there is a h, so w of I j is the weight on that h. So, weight function is also another input. So, these three are this is the input of a minimum spanning tree problem, and we have to find out a minimum spanning tree. So, basically we need to find out a spanning tree which of minimum weight. So, what do we mean by spanning tree? So, it is basically a subgraph, it is a tree. So, tree means it should not contain any cycle. So, it is a tree, basically it is a subgraph, it should not contain any cycle, and spanning meaning it should cover all the vertices. So, you should get a subgraph which must cover all the vertices. Okay. It should cover all the vertices, that way it is called spanning tree, and the weight should be minimum among all others. So, what are the spanning tree we can have from this graph? So, if this is the input, what are the spanning tree we can have? So, we can have the tree like this. So, we can have so tree should not contain any cycle. So, we can have like this. So, this one, then this one, then this one. This is also covering all the vertices and there is no cycle. So, 1, 2, 3, 4. So, this is a tree T1. Okay. So, this is the weight is minus 3, 4, 6. And so, what is the weight of this tree? So, weight of a tree is basically the sum of the weight of I j if I j is the age in that tree. This is the weight of the tree. So, we just basically do the sum of this. So, this is basically 10. So, this is weight of this is basically 7, weight of T1 is 7. So, any spanning tree we have, so we can have this tree. So, we can have this one, and this one. This is also a spanning tree. So, this is weight is basically minus 3, minus 5, minus 2. So, if this is T2, so weight of T2 is basically so minus 10, and we have another tree also like this. We can have this, then we can have like this, this, and then we can have this. So, this is also a spanning tree, and weight is minus 3 over here, minus 5, 6. So, it is not less than this. So, we can have some other spanning tree also. Among these, I think this one is the minimum one. So, this should be our output of the algorithm, the finding the minimum spanning tree algorithm. Okay. So, this is the problem. So, we have basically we need to find the subgraph which is basically tree, and not only tree, it should be the spanning tree. So, that means it should cover all the vertices and it should give us the minimum edge weight. So, that is the problem. So, given a graph, given a directed graph, we should find out this. So, given a graph, so input is a graph. So, this is the MST problem, minimum spanning tree problem. So, input is a graph G, directed graph, and we have a edge weight. So, this is the input, and the output will be a spanning tree which is a subgraph, which is a tree with no cycle, tree means no cycle, and that contain all the vertices such that the weight is minimum. Wt is the summation of W and this is the minimum among all such T. So, Wt is the minimum among all such T. So, all such we consider all such spanning tree, among this whichever give us the minimum weight, that is the minimum spanning tree. Okay, so let us take an example. So we have taken a small example, let us take a bigger example, how we can have a spanning tree of a graph. So example of a, let us take a bigger graph. So let us take little, suppose this is the graph. Okay, suppose this is the graph with these are the vertices, and let us have the edge weight 5, 14, 8, 3, 10, 7, 9, 15. Okay, suppose this is the input and this is a graph with this many vertices, and these are the edges, and this is the W, the weight function on the edges. Now we want to find out the minimum spanning tree. Now can you tell me which are the edges should be there in the minimum spanning tree? So which are the edges must be there in the minimum spanning tree? These two edges must be there in the minimum spanning tree, because this is the only edge which is connecting this node with the remaining nodes, and the minimum this is a spanning tree. So we have to cover all the vertices. So to cover these two vertices, there is no other way other than taking these two edges in the minimum spanning tree. Okay, so after taking this, what we do? So now we try to cover all the vertices. So now what we do? We just, so it covering these two vertices. Now if we take this one, it is covering these two vertices. Now we want to cover these two vertices. Now if we take this edge, it is covering only this vertex with a cost 12. Instead of that, if we take this edge and this edge, it is covering these two vertices with a cost this. So this is the intuition. So we must take these two vertices. So this is 5. Okay, so after that, so we have to cover this. Now how to cover this? We take this, because this is, now after that, to cover this we can take this. So this is a MST, this is a MST, this is minimum spanning tree. So we just use the intuition to have this. Okay, so this is a MST. Now we want to know the algorithm way how we can construct such MST. So for that we want to see whether we can use the dynamic programming technique which we know for this. So for that we need to check the hallmark for this. So basically we need to check, there are two hallmark for dynamic programming problem. So one is the optimal substructure. So that means, so let us just anyway, if we need it, we come back to this graph. So optimal substructure, whether we have this hallmark structure. So what do you mean the optimal substructure here? Optimal substructure is, suppose we have a minimum spanning tree. Let G be a graph, and suppose we have a and T is a MST. Okay. So if we have this T like this, say suppose this one, and then we have so this is UV like this. Okay. Suppose this is a minimum spanning tree which is covering all the vertices. So we have a graph which is having same number of vertices, but in the graph this is T, minimum spanning tree, and in the graph we have some more edges over there, but number of vertices are same. Now for optimal substructure what we need to do? We need to say that if we take a solution if we have a solution of the whole problem, then it contains the solution of the sub problem. So, what we do? We remove this h. Okay. So, we remove this h and then we consider this tree as T1 and this tree as T2. Now, we claim that T1 is the minimum spanning tree of the G1. G1 is the set which is induced by T1. That means, G1 contain all the edges which are basically connecting with the vertices from T1, and G2 is the all the edges which is basically connecting the vertices of T2. So, basically G is G1 union G2. Okay. So, we have to prove that T1 is the minimum spanning tree of G1 and T2 is the minimum spanning tree of G2. Then that will sufficient to show that optimal substructure is there. So, to prove that, let us suppose this is not. Suppose T1 is not a minimum spanning tree of G1. So, that means there is another tree which is a minimum spanning tree of G1. So, that is the T1 prime is a MST. So, that means weight of T1 prime must be less than weight of T1. So, what we do? We take that T1 prime and we take this H and we take T2. So, we just take this new T star which is basically T1 prime union UV union T2. Okay. And this T star is a spanning tree of the whole graph G, and the weight of T star is less than T, because weight of T star is basically weight of T1 star plus weight of UV plus weight of T2, and this is less than T1. So, basically this is basically weight of T star is less than weight of T, which contradict the fact that T is a spanning tree of minimum spanning tree of G. So, that means this T1 is the T1 has to be the minimum spanning tree of the induced graph G1, and similarly we can show T2 is the minimum spanning tree of G2. So, this is the this is satisfying the first hallmark of the dynamic programming technique, and the second hallmark is optimal substructure. With that also we can verify that there are optimal repetition of this. So, that means one can think for a going for dynamic programming technique for finding the minimum spanning tree. But in the next class we will talk about another powerful technique which is called greedy technique, greedy approach, greedy technique to find the minimum spanning tree. Thank you.